This is an example of an iterated integral, and they show up for lots of reasons, but one of the most basic is to calculate the volume under some graph, z equals f of x, y, and let's say 3 plus x squared y. Got that graph here. I'll talk about that graph in a second. Over a rectangle in the xy plane. So with interval notation, it's 1, 3 cross 0, 2, which just means that x is in this interval, y is in this interval. So x is between 1 and 3, and y is between 0 and 2. So we're going to see that this, especially since this is such a simple function, the iterated integral is actually going to be quite easy to do. Often it's the picture that's the hardest thing, and the connection between the picture and the integral. So let's see, what does this look like? Just real briefly, it's going to, if you want to graph this over a particular rectangle, well, I've got the rectangle staked out. X is between 1 and 3. Y is between 0 and, I forgot to put in a 2 there. And what is it going to look like? Well, it's a fairly simple function. One thing to do that's really useful is just get the corners. When x is 1 and y is 0, the height is 3. When x is 3 and y is 0, the height is 3. And let's get that out of the way. When x is 1 and y is 2, you're going to get 3 plus 1 squared times 2. 3 plus 2 is 5. So it goes up a bit to here. I'm trying to indicate it's going up a bit. And then when x is 3 and y is 2, that's going to be quite a bit bigger. It's 3 plus 9 times 2 plus 18 is 21. So I kind of downsized a little bit. It's really a bit more extreme. This is rather higher in reality. What else to get a good picture? If you can, once you get the corners, if you can kind of figure out what connects them, the edges, that can be useful. Well, this is nice because the slices for constant x, it's just 3 plus a constant times y. That's just a straight line of various different slopes depending on the x value as y increases. So this is a straight line. This, I didn't draw it super straight. That's a steeper straight line. Everything going in this direction parallel to the y-axis is going to be a straight line. If you set y to be a constant, you're going to get 3 plus various constants times x squared. So these are going to be various parabolas. This guy is just 3, z equals 3. So it's going to be something with parabolic cross sections going here and straight line cross sections going in the y direction. If you want to see a more official picture, I had Calplot 3D do it. Looks like that. It's about as good a picture as I could get there. You see, kind of see the parabolic cross sections in the x and then the straight line cross sections as you go in the y. But I'll go back to my by hand picture right here. Okay. So we want to get the volume of that. And the idea is we're going to slice it up. And we can choose either way of slicing. We can slice, and the floor plan. Here the floor plan is not complicated, but I always like to draw it separately. X is from 1 to 3. Y is from 0 to 2. So there it is. We're going to have much more interesting floor plans very soon, where it's really quite important to pay attention very carefully to what the floor plan looks like. And let's slice the floor plan up, let's do it this way, into slices parallel to the x-axis. So the variable that's going to collate the slices together and be the outer or second integral when we actually evaluate is going to be y. And that's going to put together all the slices like this that have a variable x and a fixed y. But then inside that, we're going to have the x integral, which for any one of these particular slices actually figures out what is the area of that slice. So the inner part is an area of a slice, then times the thickness is going to get the volume. Okay, I have a longer video if you want to watch the intro to iterated integrals that's about the idea, but let's just set it up. So y is going to go from 0 to 2, x goes from 1 to 3, and see if I can squeeze it in. 3 plus x squared y is the height. So this 3 plus x squared y dx, that integral is going to give us the cross-sectional area of each slice. Because it has a y in it, it's going to be a function of y. The x will go away because that's being integrated out, but the y will remain. Then that will all be, those will be the integral, those will be the areas of the cross-sections times the thickness, and we'll integrate that. Okay, so I know that's a lot of setup, but as I say, that's really the hard part for a lot of this. So now it's going to be easy. Not that every integral is easy, but this will be pretty good. So when you're doing an iterated integral, remember that in this integral, the dx integral, any other variable, in here particularly y is constant, and you treat it as a constant as you usually would. Okay, integral 3 dx is going to be 3x. Integral x squared y is going to be 1/3 x cubed y, all from x equals 1 to x equals 3. Usually don't write the x's, but it's a good idea the first, say, 10 times you do an iterated integral to do that. And then let's just go ahead and evaluate that. We're going to start getting some fractions. We're going to get 9 plus 1/3 times 3 cubed. Nice, that's 9. 9 plus 9y minus 3 plus 1/3 y. We're going to simplify that before we integrate it. Let's go up top. And integral 0 to 2. Okay, so we're going to get 6 plus 26/3. Oh well. I didn't engineer it to have the numbers be super, super simple, but it's not like it's a hard integral. Okay, right here, that does have a meaning. This is the cross-sectional area, and it makes sense that it's an increasing function of y. As y goes up this way, away from us, from our viewpoint here, those slices certainly do look like they're getting bigger, and they are. Okay, and now we get to integrate that in y, and we get 6y plus 13/3, not 13/13ths, 13/3 y squared, all from 0 to 2. Luckily, the 0 just dies, and we're going to get 12 plus 52/3. Might as well do a common denominator, 88/3. And that's the volume as an iterated integral.